It is important that we stick to the steps because this is an example where the common bonding pattern is violated left and right, literally, okay? So here's what we have. CO. Carbon brings us 4 electrons. And oxygen brings us 6 electrons. Altogether, we have 10 electrons, valence electrons, meaning 5. All right. Now, here's where you need to pay attention, all right? I have 5 electron pairs. I already used one of them. When I distribute the rest of the electron pairs, I'm going to prioritize oxygen, okay? I have 1, 2, 3, 4. And the fifth one, I cannot give it to oxygen because oxygen already has 8 electrons. Therefore, fifth pair must go on carbon. Okay. Now, I have an octet of electrons on oxygen, but on carbon, I only have 1 lone pair and 1 bonding electron pair, meaning only 4 electrons. So what do? We share these lone pairs with carbon so that carbon can have an octet as well. So we can share or delocalize these electrons. And when we do that, we are going to see that we're going to have a triple bond between carbon and oxygen, right? And then 1 lone pair on each of them. Therefore, this is our Lewis structure of carbon monoxide. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Now, one thing, right? When I distributed my electron pairs, I prioritized oxygen. Can somebody tell me why? Why did I give electrons first to oxygen? William? All right, let's go ahead. Can I have? Okay. William, why did I prioritize oxygen when I distributed my electron pairs?
Because it's more electronegative. It
look at that.
Electrons more.
Oh, okay. All right. Yeah, that's exactly right. But I'm going to come to that word in a minute. Now, again, please pay attention. I'm going to have this in your quiz tomorrow. Okay. All right. Now, why did I give electrons to oxygen first? Because oxygen has more protons in the nucleus, meaning more positive charge, greater attraction towards the electrons compared to carbon. Therefore, when I give the electrons first to oxygen and then to carbon, in this situation. Okay. Why? Oxygen has more attraction towards the electrons, and that is defined by, like William said, the idea of electronegativity. Okay. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions? All right. Here's another thing that we can think of. Okay. You know what? I'm going to ask you this. Okay. So I'm going to redraw my carbon-oxygen bond. Let's make just one bond. Let's say that we have a carbon-oxygen bond. All right. Here's a question for you. A whiteboard question. These bonding electrons, will they spend more time around carbon, oxygen, or at the center? Go ahead. One more time. The bonding electrons indicated by this line, right? Will those electrons spend more time around carbon, oxygen, or at the middle? Go ahead. On your whiteboard, I want to see the answer. Oxygen in many cases. All right. Can someone tell me why though? I like it. Remember your name is one more time.
Marissa.
Melissa? Melissa, can you tell me why?
Because it has more protons, so it attracts more electrons.
Thank you. That is it. Right? Between carbon and oxygen has more protons in it. Therefore, those electrons will be more attracted towards the oxygen nucleus compared to carbon. All right. So it's just like okay. So if your mom has more money than the dad, you're gonna spend more time around mom than the dad, right? Something like that. Anyway. Okay. Anyway. So. All right. Now here are the implications here. I was kidding. You will spend more time around dad anyway. All right. Now, now here are the implications of that. Okay. So as a result of that, you are going to have a higher electron density around oxygen and a lower electron density around carbon. That's the implication here. Okay. Here's another question for you, everybody. Okay. If you have a higher electron density, what will be the charge around oxygen atom? If you have more electrons around oxygen, what will be the charge around oxygen atom? Thank you. Electrons are negative, therefore, around oxygen, you will have a higher negative charge. Okay? So we're going to indicate that by saying that we have a negative charge. That is actually a partial negative charge. Okay? And the partial charges are indicated by the lowercase Greek letter delta. Okay? Delta negative around oxygen. All right. Here's a follow-up question. What will be the partial charge on carbon then? Partial charge on carbon should be everybody. Everybody. Thank you. Positive, partially positive. Why? It has less electrons now because oxygen is pulling away the electrons. Okay. Therefore, the partial charge on carbon will be positive. Now I'm going to define, just to make sure that everybody's on the same page. When I say delta positive, this means positive partial charge. Okay. When I say delta negative, this means negative partial charge. Okay. Now here's what we have now as a result of this. We have a dipole. Or in other words, we have a charge separation. Whenever we have a charge separation like this, or partial charge separation like this in a bond, we say that our bond is, anybody? Thank you, polar. Okay, this is the idea of polar bonds. Right? So this is how we get polar bonds. You have a partial charge separation. Why? Somebody is pulling electrons towards it more than the other. As a result of that, it's going to get the partial negative charge. The other one is going to get the partial positive charge. Right? And then this bond polarity is, actually, we are going to be using a lot of Greek letters today. It's like, a Greek class, okay? The bond polarity is given the Greek letter mu. Right? And this is also known as bond dipole moment. Bond dipole moment, okay, aka bond polarity, also known as bond polarity. Okay, and here's what we need to know about the bond dipole moment. Bond dipole moment is a vector. Okay, if it is a vector, okay, what properties do we have in a vector? Thank you. Vector should have a direction, okay, as well as a magnitude. Okay, so the dipole moment vector or the bond dipole moment always goes from. Can I borrow a red pen from somebody? Sophia, do you have a red pen that I can borrow? Perfect. Okay, I'll figure it out. Okay, so the bond dipole moment always goes from partial positive atom to the partial negative atom. So in other words, the arrowhead, okay, always goes towards the partial negative atom. Okay, the arrow tail, I'm going to also indicate like a positive sign over here, so that there's no ambiguity, is always by the partial positive atom. Okay, so this is my bond dipole moment. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? All right. Now we know This all happens because one atom has more attraction towards the electrons than the other. As a result of that, the bonding electrons spend more time around that atom compared to the other. Now, it turns out the ability of bonding electrons to spend more time around a certain atom is given by this idea called electronegativity. Okay, I'm going to come back to this page. Okay, so electronegativity is given to you in a table called Pauling electronegativity table. It looks like this. Okay, so in this table you can see that fluorine has the highest electronegativity of any element, of 4.0. It's like fluorine has the highest GPA in the class, 4.0. Everybody else has a lower GPA than I'm sorry, electronegativity than fluorine. Okay? Fluorine is 4.0, oxygen is 3.5, chlorine is 3.0, and so forth. Okay? So for the first approximation, if you want to see a trend here, the only trend I see here is, let me actually draw it for you. I see that electronegativity increases diagonally towards fluorine. All right? So as you get closer to the fluorine, electronegativity value also increases. Okay. All right. Any question about the electronegativity? Okay. So electronegativity, higher the value, more likely it is for the bonding electrons to spend more time around it. That is what is meant by electronegativity. All right. Any questions, concerns, comments? I'm going to write one last thing and then we're done. Like, then I'm done talking. You'll be doing almost all the talking after that. Right? And that last thing is the magnitude of the bond dipole moment or bond polarity. Okay, the magnitude of the bond polarity depends on mainly one thing, and that thing is, I'm going to write this down. Okay, the bond dipole moment magnitude. I'm going to write it like this. So here's the bond dipole moment mu. The magnitude of that, I'm going to indicate this in 2 lines like this because I only care about the magnitude, not the direction here. That's what it's meant by this. Okay, absolute value, in other words, okay, is directly proportional to, pardon my Greek here, delta chi. Okay, so what do I mean by delta chi? So chi is the electronegativity value. Chi is electronegativity. Okay. So delta is usually used to signify the difference or the change. Okay. So when I say delta chi, let me write that out for you. When I say delta chi, but by the way, this is like x, but it's not x. It's like chi, it is chi because you have this weird thing going on, and it's like chi omega. I don't know, it's something like that. Anyway, chi. Okay. Anyway, so what is meant by delta chi is the difference between electronegativity values. Electronegativity values. Okay, that's the main thing that determines the magnitude of the bond polarity or magnitude of the bond dipole moment. Okay. In rare cases, this is just for the completion of our notes. Okay, in rare cases where delta chi doesn't cut it, all right, we are going to be looking at the bond length. All right, so I'm going to call it, let's call it bond length. Bond length. By the way, I wrote this in pencil not because I ran out of ink in my blue pen. Can somebody tell me why I wrote that in pencil? William, do you know why? Because it is not that important. All right? Because the most important thing that you need to focus on is the delta chi, right? And I haven't seen any questions in exams or quizzes where you have to resort to bond length to determine the relative bond polarity. Okay? But for the completion of our notes, I mentioned that. I'll do one example and then that's it. All right, that is it. What questions, concerns, comments do we have? Yes, miss. Thank you. Alex, is that right? Yeah. Can I have the microphone with Alex, please? All right. There you go. Alex, go ahead.
Can you just like quickly re-explain bond polarity, like the definition of it, and like
Oh, I don't care about the definition. Bond polarity is whenever we have a charge separation. Okay, one atom has a partial negative charge, other one has a partial positive charge, then the bond is polar. That's it. Yes. Huh? Yes. All right. Now, here's a question for you. Again, the whiteboard question, then we're going to switch to top pad. Say that you have two bonds. CO bond and CF bond. Okay. CO versus CF. Which bond is more polar and why? Go ahead. You have the electronegativity table on top pad, I believe. Which bond is more polar and why?
You named
Which bond is more polar? I see mainly CF. Right? CF is more polar. Thank you. Very good. CF is more polar. Thank you. Exactly. Delta chi is greater. All right. Now here's how we did that. One more time, everybody. Okay. So if we wrote the chi values or electronegativity values, carbon is 2.5, oxygen is 3.5, carbon is still 2.5, fluorine is 4.0. Okay. Therefore, delta chi or electronegativity difference for, I only care about the absolute value. For CO bond is 1.0, 3.5 minus 2.5 is 1.0. For CF bond, it is 1.5. Because you have a higher electronegativity difference in CF bond is more polar. That's it. That is, greater the electronegativity difference, higher the bond polarity. Okay. Remember, here we are talking about the bond polarity. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? All right. So with that, let's do the same thing in top hat.
Yeah, maybe.
All right. By the way, here's a prettier picture of the same thing. Okay. When you have one atom more electronegative than the other, that atom will get a partial negative charge, the other atom will get a partial positive charge, and the dipole moment vector will go from partial positive to partial negative. Again, that's what this arrow indicates. Okay, now we have a polar bond. And then the magnitude of the bond polarity depends on two things. And then those two things are delta chi or difference of electronegativities, okay, and the bond length. Okay, and then we wrote the same thing in our notes. Like this. Okay, it's the same thing we have in our notes as well. All right. So keeping that in mind, I didn't mean to do that. What I want you to do is I want you to tackle this question. All right. Here are some molecules with some bonds. For an example, CF4 have CF bonds. Okay. And CO2 have CO bonds. NN bonds. I mean, I know it's a triple bond, that's okay. And then CH4 has CH bonds. H2O has HO bonds or OH bonds. And then SO2 has, you're going to determine that, okay? What I want you to do is I want you to arrange the bonds from weakest to highest bond polarity. Go ahead. Lowest to highest bond polarity, right?
Yeah.
So in N2, we have a bond between two nitrogen atoms. Is it it doesn't matter how many bonds we have. It's a triple bond, we know that, but it doesn't matter to us. Okay, we have a bond between N and N. In CH4 we have CH bonds. In CO2 we have a bond between C and bonds between C and O. In SO2 we have bonds between S and O. In H2O we have bonds between H and O. In CF4 we have bonds between C and F. Okay, and then I write the electronegativity values. So, or chi values. So nitrogen is it 3.0? I think it's 3.0, right? Okay, it doesn't matter anyway. So nitrogen is 3.0, 3.0, carbon is 2.5, hydrogen is 2.1, carbon is 2.5, oxygen is 3.5, sulfur is 2.5, oxygen is 3.5, hydrogen is 2.1, oxygen is 3.5, and carbon is 2.5, fluorine is 4.0. Okay, and then the delta chi or difference between them for NN bonds is 0. This is 0.4. This is 1.0. This is 1.0. I only care about the absolute value here. Okay, and then HO it is 1.4, and then for a CF bond it should be 1.5. Okay, so based on the electronegativity difference, okay, the most polar bond is CF. Let me indicate that. Okay, we have the most polar bonds in CF4, and then H2O, then CO2 and SO2, then CH4, and N2 has the least polar or non-polar bonds. Okay, and then between CO2 and SO2, they both have the same electronegativity difference. Okay, therefore delta chi doesn't cut it. Therefore, we have to resort to the bond length, right? How do we determine that? So sulfur is in the third period. Okay, carbon is in the second period. Okay, because you have more shells in sulfur, sulfur is a large atom. All right. So if carbon is this much, this is my carbon. Okay, sulfur is this much. Okay, oxygen is the same in both cases. This is oxygen, right? Here's oxygen. Okay, so therefore the bond length of CO is this much, and the bond length of SO is this much. Okay, so SO has a longer bond compared to CO. Therefore, we can expect SO bond to be more polar than and CO bond. Yep. All right, I'll give you 30 seconds to think about this, and then if you have any questions, concerns, comments, I'll take them. All right, go ahead. Check with each other. I mean, do a gut check. Okay. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Okay. So remember, in this case, it's essential that you read the question. The question is asking about the bond polarity. So we do not, overcomplicate things to our things by, thinking about the molecular polarity. Right, but I know some of you were thinking about, the CF4 has 4 bonds now. So what do I do? Multiply them, add them, subtract them. We're thinking about those. Okay, the idea is it doesn't matter because they're talking about the bond polarity here. Okay, so but now at some point we need to address the elephant in the room, right? What about the molecular polarity? Right. So here it takes care of the bond polarity, but let's move on to molecular polarity, right? So let me write this down. Molecular polarity, okay? So for this, I'm going to give the Greek letter mu, but I already used mu for bond polarity. So therefore, I'm going to call this mu sub net or net dipole moment or mu net. Okay, and then now I'm going to write something here. Do not get alarmed because I'm not going to make you calculate weird things here, like using vector algebra or something like that. I don't even know what that is. Okay, so don't worry about it, but here's how it goes. The mu net or the net dipole moment is, okay, mu net is equal to, and in mathematics, how do we indicate the summation? What do we use? What Greek letter do we use for summation? Come it again? Like sigma, right? Okay, uppercase sigma, yeah. So the sum of the bond dipole moments. I'll write this down as well, okay? So mu net or net dipole moment is the sum of bond dipole moments. Okay. So I mean, I'll even write this. This is the net dipole moment, or molecular polarity. Net dipole moment, aka molecular polarity. Molecular polarity. All right, here we go. That's it. All right. So whenever we want to find out the molecular polarity of the net dipole moment, we just add up all the bond dipole moments. That's it. All right. Here's an example. I'm going to do one on my notebook and then switch to the PowerPoint or the top hat. So let's think about CO, right? CO2 actually. CO2. All right. So CO2, we know it's essential that we write or draw the molecule to the correct geometry. Okay. We know CO2 has what molecular shape? What's the shape of the CO2 molecule? Thank you. It's a linear molecule, right? So it looks like this. Okay. But we know between carbon and oxygen is more electronegative. Therefore, oxygen will get the partial negative charge and carbon will have the partial positive charge. Therefore, if you draw the bond dipole moments, okay, here's one going from the positive atom to the negative atom. Okay, here's the other one going from positive atom to the negative atom in the opposite direction. Okay, these are vectors equal in magnitude but opposite in direction. So let's add them up. Okay, so mu net is equal to this vector added to this vector. What do I get if I add this up? Thank you. This adds up to 0. Okay. Therefore, mu net or net dipole moment is 0. Therefore, what can you tell me about the polarity of CO2? Is it polar or non-polar? Thank you. CO2 is a non-polar molecule. Therefore, CO2 is non-polar. It has very strong polar bonds, but because they cancel each other out, okay, the entire molecule is non-polar. Right? All right. What questions, concerns, comments do we have at this moment? Anything? Any questions at this point? All right. So let's do this. Let's keep doing this. Okay. Let's do the same thing with. Oh, by the way, okay. So dipole moment is a vector, just like displacement. All right. So in CO2, it's just like me walking like I don't know, to my right, 1, 2, 3, 4, 5, and turn around, like okay, and then walking the other way, 1, 2, 3, 4, 5. I ended up at the same place I began, right? Therefore, my net displacement is 0. Okay. Same thing goes on here. Okay. So you go one direction, okay, a similar amount, and then the other direction, the same amount. So your net displacement or your net vector is going to be 0. That's what happened there. All right. Now with that, let's have some fun with this. So let's do this. Okay. Let's think about H2O. Okay. Here's H2O. Okay. Okay. So can we determine whether H2O is polar or non-polar? I'll give you 30 seconds to think about this. And come. Here's what you need to acknowledge here. Please pay attention. You're going to see this over and over, throughout Chem 151 and then 152 as well. Okay. So between hydrogen and oxygen, which one is more electronegative? Hydrogen or oxygen? Thank you. Oxygen is more electronegative. Hydrogen is 2.1. You don't have to memorize them. You will have access to a table during your exam, but for quizzes and online exams, it's open notes, so you should have them handy. Okay. Hydrogen is 2.1. Oxygen is 3.5. Therefore, oxygen has a higher electronegativity, meaning in this molecule, oxygen will get the partial negative charge. Okay. Hydrogens will have the partial positive charges. Number one. Okay. Then I draw the bond dipole moments. All right. So please pay attention for a second. Okay. So I always go from the partial positive atom to the partial negative atom. Okay. Here's one. Here's the other one. I drew my bond dipole moments. Okay. Then I need to add them up. How do I add them up? Okay, so maybe you have learned this somewhere. Okay, I mean, I don't want to use this term like, I don't know, vector algebra or something like that. It doesn't matter. Okay, so how do we add them up? By arranging them head to tail. Here's what I mean by that. Here's here's one vector. Okay, the other vector I'm going to draw from head to tail. Okay, so here's the head of one vector kissing the tail of the other vector. This happens all the time in dog parks. Okay, so it looks like this. Now, what do I see here? We started at, I'm going to use red. Okay. We started at this point. This is our origin. We ended up at this point. Okay. So we have a net dipole moment going from, from over here, starting point to the end point. Therefore, the net dipole moment of this molecule should look like this. The direction should go towards oxygen like this. Okay. Right. So what do I write here? Just for the completion of our thoughts. Okay. I'm going to write mu net or net dipole moment is not zero. How do I know it is not zero? Because it did not come back to the origin. All right. Therefore, it is not zero. Therefore, this molecule is polar. Right? All right. What questions, concerns, comments do we have at this point? We'll do more examples. It will be much easier when we do more of them. All right. So let's do SO3. Okay. I want you to tell me whether SO3 is polar or non-polar. Go ahead. Draw SO3 on your whiteboards. And then let me know whether it is polar or non-polar. SO3. SO3.
Right, so
Sulfur trioxide. SO3. You might want to use the hybrid structure. I know it has resonance. Oh, you already have that. Wonderful. Okay. Yeah, I think some of you already figured out that you have access to this simulator. So SO3 looks like this. Here's SO3 on the screen as well, in case you wonder. But you should be able to draw them now, okay, on your whiteboard, so somewhere. I'm going to do this on the screen once, and then, and then we can discuss, okay? So between sulfur and oxygen, which one is more electronegative? Sulfur, oxygen. I need the feedback from everybody now. One more time, okay? Between sulfur and oxygen, which atom is more electronegative? Thank you, oxygen, right? So therefore, our partial negative charges will be with oxygen. Okay. Oxygen will have the partial negative charges, and the sulfur will have the partial positive charge. Okay. Therefore, if you drew your dipole moment vector, so bond dipole moments, you're gonna get one like, oops, sorry. Okay. You're gonna get one like this, other one going this way, the other one going this way. Okay. And if you arrange them head to tail, here's one, and here's another head to tail. Head is kissing the tail, and then here's the third one. All right. You see that we came back to the origin, meaning our net displacement or net vector is 0. Therefore, you slide that down. New net is 0. Therefore, SO3 must be non-polar. That's it. All right. What questions, concerns, comments do we have at this moment? Anything? Right? So all you have to do is draw the bond dipole moments and arrange them head to tail. That's it. Okay? So I'm going to emphasize one more thing. If you can pay attention for a second, okay? It is true. It's really important that you draw the molecule to the correct geometry. If you don't do it, you're going to get them wrong. Okay? Here's an example. So I saw some of you drew water, okay? H2O molecule like this. So if you drew H2O molecule like this, please pay attention for a second. Okay? So oxygen is more negative. Therefore, you're going to have two dipole moments going towards oxygen like this. Zero. Unit will be 0. Okay? Making water non-polar. All right? But you know that this is wrong. Why? Water is not a linear molecule. Water is actually a polar, a bent molecule like this. As a result of that, our bond dipole moments go towards oxygen like this. Okay? So if we add this up, you're going to have the net dipole moment going towards oxygen, okay, like this. So your tail would be in between the two hydrogens, okay? Therefore, mu net is not 0, is not equal to 0. It should be polar. All right. So it is really important. I can emphasize this enough that you draw the molecule to the correct geometry when you do this. Otherwise, we're gonna, we're gonna have problems. All right. Any questions, concerns, comments at this point? Let's do one last thing, then we are done. Okay, with this. All right. Let's do CH4. No, not CH4. CF4. Basically the same thing. All right, CH4 or CF4 or CCl4, whatever. Okay, so this is CF4. Everybody knows that fluorine is green. I'm sorry, nobody knows. I was kidding. So these are fluorine atoms. So these are CF4. Can you let me know whether this is polar or non-polar? Go ahead. Draw this now because it's a 3D molecule. Okay, but I don't have that problem. It's already there on the computer screen. Well, I'll show you a trick in a minute, okay? All right. All right. So first things first. Now, first thing that you need to do is to determine the electronegativity values, okay? So using a table from internet or ChatGPT or something like that, okay? So between carbon and fluorine, fluorine is more electronegative than carbon. As a result of that, our fluorines will have a partial, thank you, partial negative charge. Okay, fluorines are partially negative. All right, that's the first thing I would do. Okay, and my carbon would be partially positive. Number one. Okay, then I draw my bond dipole moments. So I have one going up like this. 1, 2, 3, and 4. Okay. All right. So I'm going to crash and burn here. Okay. It's really hard to draw this, Anyway, so here's one. Here's that kissing the tail of the other one. And here's the third one. And here's the fourth one. Okay. You see that we came back to the origin, meaning our net displacement is 0. Okay, mu net is 0, meaning our molecule is non-polar. Okay. The point is this. Whenever you have a perfect tetrahedral molecule like this, okay, it's going to be a non-polar molecule. But as soon as you replace one of those atoms with something else, I'll give you an example. Okay, say that you replace one of these fluorines with, say, hydrogen. Okay, it's going to become polar. Okay, so keep that in mind. So any tetrahedral molecule, it can be CH4 like this, it can be CCl4, CF4, CBr4. If it is tetrahedral, okay, that means you have the same atom on all corners, then it's going to be a non-polar molecule. But if you replace any of them, any atom by anything else, okay, 1 or 2 or 3 atoms by anything else, it's going to become polar. All right. So I'll even show you the net dipole moment of one of them. I'm going to clear this. Okay. Here's CHF3. Okay. So here we have, if you draw the bond dipole moments, we have 1, 2, 3 dipole moments going towards the fluorines downwards, and then between carbon and fluorine, carbon and hydrogen, carbon is more negative. Therefore, that dipole moment should be going towards carbon like that. So you can see that all my heads, all my partial negative charges are downwards, meaning this molecule has a net dipole moment going towards the 3 fluorine atoms like this. Okay, the head of my net dipole moment should be in between the 3 fluorine atoms. Therefore, this should be the direction of my net dipole moment of this molecule. I only did one. Okay, only one thing. I replaced fluorine with the hydrogen. It became polar. All right. What questions, concerns, comments do we have at this moment? Okay, so we wrote 2 things. Okay, from this exercise. All perfect tetrahedral molecules. Okay, that means you have 4 atoms, 4 similar atoms bonded to the carbon, okay, are going to be non-polar molecules. Okay, why? The net dipole moments cancel out to 0. Okay, as soon as you replace any one of them with any other atom, it's going to become a polar molecule. That's it. All right, any questions, concerns, comments at this point? Okay, so I'm going to clear my doodling, and then I'm going to point out one other thing. Oh, here's the same thing done in the slide. Okay, they add up to 0, okay, which is wonderful. All right, now let's try this question. Here we go. Tetrachloride, SiCl4 for you. Okay, I'm going to close this question in 5, 4, 3, 2, and 1. All right, before I look at your answers, okay? So CS2 is just like CO2 because sulfur and oxygen are in the same group. You can expect that to be linear as well. So it should look something like this. All right, this should be my CS2. And then SCl2 is like OCl2, OF2, OH2, or something like that. So it has to be a bent molecule. Okay, that looks like this. Cl. And Cl, you have 2 lone pairs on the sulfur. Okay, so here we have a perfect tetrahedral molecule. We know mu net is 0 here. Okay, therefore non-polar. Non-polar. All right. So here, I know between carbon and sulfur, there's no electronegativity difference. Okay. Even there was, if there was electronegativity difference, Those will cancel each other out. Okay. Therefore, mu net is 0. Therefore, it should be non-polar. Okay. And then between chlorine and sulfur, chlorine is more electronegative than sulfur. Chlorine is 3.0, sulfur is 2.5. Therefore, chlorine will have a partial negative charges like this. Sulfur will be partially positive. Therefore, the net dipole moment of that should look like this. Should be going towards 2 chlorine atoms. The head must be in between the 2 chlorine atoms. So mu net is not 0, meaning polar. Okay, that's it. All right. Any questions, concerns, comments at this point? Okay. So now I want to do one other thing actually for today. Okay. So after some time, okay, like me, you're gonna get lazy, right? Right now you want to do everything, right? But so it turns out we can analyze the symmetry of the molecule and determine whether the molecule is polar or non-polar, because it's all about charge distribution. If the charge distribution is symmetrical, then the molecule is non-polar. If the charge distribution is asymmetrical, then the molecule is polar. All right. Here are examples. So we know any tetrahedral molecule, we have a symmetric distribution of charges is going to be non-polar. So if you take something like hexafluorobenzene, all right, you have symmetric distribution of charges. Okay, therefore it's going to be a non-polar molecule. Also, you can think of, right? You have carbon fluorine, like bond dipole moment going this way, another one going this way. They cancel each other out. One going this way, another one going this way. They cancel each other out. One going this way, and that will be cancelled out with the one going the opposite way, like that. Okay, so when you have symmetric distribution of atoms or charges, they cancel each other out. Therefore, they're going to become non-polar. Here's another example, just like carbon dioxide. Okay, acetylene is non-polar. Okay, and and so forth. What about this guy, dimethyl ether, polar or non-polar? William, what did you say? Yeah, it's a polar molecule because you don't have the symmetric distribution of charges, right? You have a clear high electron density on this area around oxygen. It should be partially negative. The other side should be partially positive. Therefore, you should have a net dipole moment going towards oxygen in this molecule. Therefore, this should be polar. Why? The distribution of charges are not symmetrical. Okay, that's why this became polar. So the point is, you can look at the symmetry of the molecule and determine whether the molecule is polar or non-polar. Okay, so that's the point of this slide and then this activity as well for fun. Here we go. Here are some molecules. I want you to analyze the symmetry of them and determine whether they are polar or non-polar. If you have time, I'll show you a question that you're going to see on the quiz tomorrow. Like, a similar question. As our last activity for today. All right, we have close to 90% answers. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right. Now, from experience, I know that we have clicked on everything, but you're going to see that, most of you have clicked on 4 answers. Okay, you have a higher density for this, and this. These are the correct answers as well. Why? Due to symmetry, these are non-polar molecules. Okay, as opposed to this guy, we have a dipole moment, net dipole moment going this way. Therefore, it's going to be polar. Here, these two cancel out, but there's another one that doesn't cancel out. Therefore, this is going to be polar. And this one, all these 4 are canceling out, but not this guy. Therefore, it's going to be polar. All right. So this is how we use the symmetry to analyze the determine whether they're polar or non-polar. Last question. This is what you're going to see on the quiz as well. Here we go. So here's the way I would think about this. So nitrogen is the most electronegative atom here. Therefore, nitrogen must have the partial negative charge. Okay, nitrogen must have the partial negative charge in all these options. Okay. If that is the case, the arrow tail cannot be with nitrogen. Okay, so therefore option A is out. Why? We have the arrow tail by nitrogen. Option B is out. Why? The arrow tail is with nitrogen. It has to be the arrow head with nitrogen, not the arrow tail. Okay, so between C and D, so D shows the bond dipole moment of the carbon nitrogen bond, not the net dipole moment. But you know, carbon is partially positive, hydrogen is partially positive, and these are partially positive. Therefore, the arrow tail must be in between the two hydrogens and the carbon. Therefore, option C must be the correct answer, not D, because D is only showing the bond dipole moment, not the net dipole moment of this group. So this should be your answer. All right. I hope you have fun tomorrow with the quiz. I'll